Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is the MAC addresses video. And this is actually a topic we're going to revisit in a later video in this course when we talk about switches. But before we talk about how switches handle MAC addresses and how they're used by the switch, we need to make sure we know fundamentally what they are, how they're built, what their address format is. And we're also going to talk a little bit about hexadecimal conversion. And if that phrase, if you go, what? Or if it intimidates you a little bit, don't worry about it. You're actually going to find that working with hexadecimal, or hex as we usually call it, is actually very simple. But you need to be able to look at a hexadecimal character and convert it into decimal, which is what we use commonly every single day. You'll see very quickly that it's a very simple process. After that, we're going to talk about the Address Resolution Protocol, ARP, and exactly what address is being resolved there, what it's being resolved to, why we have to use it, and its very close friend, Proxy ARP. For the Network Plus exam and to know what's going on in a real-world network, you've got to know what ARP is, you've got to know how it operates, you've got to know when Proxy ARP is needed. We're going to go over all those details in this video. And we'll talk very briefly at the end about reverse ARP. Reverse ARP is almost extinct, not quite yet, so you still need to know what it does. But if you are familiar at all with DHCP, you'll see very quickly the similarities between the two. But first, let's talk about how MAC addresses are used to begin with and what the importance of MAC addresses is. Now, whether you've got networking experience, whether you're relatively new to it, you're familiar certainly with an IP address. And we're going to talk about those later in the course. But one thing that you'll notice as you get deeper and deeper into networking, you'll be doing some traffic filtering, you'll be configuring a router to send traffic destined for one IP address in one direction and another IP address in another direction. The key there is that we're always working with IP addresses to the point where we tend to forget how important a MAC address is. If host A wants to send data to host B, for example, and let me bring up a little drawing here. In this scenario, host A wants to send data to host B. And again, we tend to focus only on the IP address. But for host A to successfully send data to host B or to any host in the network, it not only has to have a destination IP address, it's got to have a destination MAC address as well. MAC addresses are just as important to the entire data transfer process as an IP address is. But again, since we tend to work more with IP addressing and the other network features and more advanced network features, we tend to forget about MAC addresses. But you will not forget about MAC addresses once we're done with this section, I promise you that. Just again, I want to remind you that for a source to send data to a destination, it's got to have a destination IP address, and it's also got to have a destination MAC address. Now, under the MAC address names here, one thing that confused me when I started studying networking, I mentioned in the previous video that we really like to have two names for almost everything in this business, just to keep it interesting. Well, with MAC addresses, literally we have 6 different names they can be known by. A MAC address is one of them. The reason for this is that MAC addresses are found at layer 2 of the OSI model, and that is the data link layer. They're often referred to as layer 2 addresses or simply L2 addresses for that very reason. And they're also called physical addresses, but I want to remind you here, that is not because MAC addresses are found at the physical layer of the OSI model, because they're not. MAC addresses are sometimes referred to as physical addresses because the address is physically burned into the network interface card itself. It physically exists on there. If you open a router up and you pull the cards out of it, you're not going to see IP addresses actually physically existing on the network card, but you will see a MAC address. Now, there are NICs now that allow you to configure your own MAC address. And we're going to talk about that because that can be a little dangerous. But right now, I just want you to keep in mind, when you hear the term physical address, what they're really talking about is the MAC address itself. Another name I mentioned there, hardware address, so named because it is burned into the hardware. And BIA stands for burned in address. And that is another term for a MAC address. So we've got 6 different names: MAC, L2, Layer 2, physical, hardware, and BIA. And like I said, sometimes we just like to make things a little more complicated in this business than perhaps we should. So just be aware that all 6 of those names are all referring to MAC addresses. So once we've got that out of the way, we need to know how a MAC address is built in the first place. And I'm going to show you a sample MAC address in just a moment. And then we're going to talk about the organizationally unique identifiers, also known as OUI, and the device ID. But before we do that, I'm going to give you a little tutorial here in hexadecimal conversion. And I want you to know first off what these hex characters mean. Because let's take a step ahead here just one time, and we're looking at a typical MAC address here of AF14B3C21445. And you can look at that and say, okay, I know what the numbers mean, but what's with the lettering? You know, where's that coming from? Well, theoretically, as that screen mentions, every single hardware device in the world should have a totally unique MAC address. And if you open a router up, if you open a printer up these days, they've got NICs, they've got network interface cards. They should, all their interfaces on a router will each have the Ethernet interfaces, that is, will have unique MAC addresses. So that's a lot of addresses if you look at all the devices around the world. So to increase the number of addresses but keeping the same number of bits, that's why MAC addresses use hexadecimal, because you can actually express a larger decimal that would take 2 bits, 10, 11, 12, and instead express them with one letter, A, B, or C. So that's why I've got that little chart right there. When you see the letter A in a MAC address, that is a representation of the decimal 10. B is 11, C is 12, D is 13, E is 14, F is 15. By the way, F is as far as it goes. There is no G equals 16, because just as our decimal system is built on the power of 10, then the hexadecimals are built on powers of 16. And let me show you what I mean by that. That sounds, you know, pretty complicated, but it's really not. Let's take a look at the decimal 134. You know, we tend not to think about this because we use the decimal system every day. So we do not look at 134 and think about what that actually means. What it actually means, if we break it down, is that we have 4 units of 1, 3 units of 10, and 1 unit of 100. But hexadecimal doesn't use powers of 10 as we go up. It's going to use its base 16. So instead of going 1, 10, 100 from right to left, it actually goes 1, 16, 256. Let's take an example of that, and let's use 130. Let's use 134. Well, in decimal, if we were presented with a decimal 134, I'll put it here again too. That simply means 1 unit of 100, 3 units of 10, 4 units of 1. Now the hexadecimal character is going to be a little different. If you were presented with the hexadecimal 134, that actually means we have 1 unit of 256, 3 units of 16, 4 units of 1. Pardon me for moving the screen down there. And 4 units of 1. Now, where did I get that from? Again, we're using base 16 here instead of base 10. So we're going to go from right to left. When we look at a hex character such as 134, this is units of 1, this is units of 16, and this is units of 256, which is 16 times 16. So if you were asked then to convert the hexadecimal character value 134 into into decimal, all you do is just write it out like that. I've got 1 unit of 256, 3 units of 16, and 4 units of 1. So that would give us 256 plus 48 plus 4. And you just add them right up. I believe that's 308. And that's all there is to it. Just takes a little bit of practice to get used to it. That's really all there is to it, though. So just a little extra tutorial there in performing hexadecimal to binary conversions. I do that here. I don't expect you to see any of that on Network Plus. You will find it helpful on other certification exams. But again, I just want you to know what those letters mean and what they stand for. So let's take a look at that MAC address again, a typical MAC address, and some things to look out for. Again, here's our typical MAC address, AF14B3C21445. Want to mention to you here for the first time, and I will remind you before the end of this particular video, if you ever see a MAC address expressed to you in a book or in an exam, I don't care where it is, where you've got a letter that comes after F, that's an invalid address. That literally cannot happen because F is a representation of the decimal 15, and it is the highest possible value for a MAC address. So if you see a G or an H or an I, anything after F, it's an invalid address. Again, theoretically, every single hardware device in the world should have a totally unique MAC address. Now, how in the world do we make that happen? Well, the first half of this address is the organizationally unique identifier, the OUI. It's not pronounced we. This is not French class. It's just spelled out OUI. And this particular OUI is going to be assigned to one vendor and one vendor only. And by vendor, I simply mean the company that is manufacturing the hardware, whether it's Cisco, whether it's Nortel, whether it's Microsoft, doesn't matter. The first half of that address, in this case AF14B3, is the OUI, and that's where the name organizationally unique comes in. Only one organization in the world is going to have that particular OUI. Now the second half of the address is a combination of hex characters that this particular vendor hasn't used yet with that particular OUI. And that's where it's truly unique, because the first half of a MAC address can only belong to one vendor anyway, and the device ID has to be an ID that that vendor has not yet used with that particular OUI. So that's how we can guarantee that it is unique. And the term you hear for that a lot is device ID. That's more of a theoretical term, a book term, than something you actually hear about a lot in the field. But you do need to know that and how to break down that typical MAC address. Now let's take a look at MAC broadcasts. And if this is a term you're not familiar with, you're not familiar yet with broadcasts. A broadcast has a destination of everyone. I want everybody to get this message that I'm about to send out, so it's a broadcast. If I'm only sending it to one destination, it's a unicast. Now, broadcasts are very important to understand. Of course, the basic is very simple, but we're always concerned with limiting broadcasts on a network. And keep that in mind as we go through this course and as you take other certification courses. Layer 2 broadcasts tend not to be much of a problem, but Layer 3 broadcasts, as you'll learn at the routing layer of the OSI model, can be pretty bad. There's one MAC broadcast address that you need to know, and that is the all Fs broadcast address. When a host is sending a data that is a layer 2 broadcast, the destination is going to be all Fs. And I put that in upper and lower case there for you. There's a misconception that a hex character value changes when it goes to uppercase, and that's not the case, no pun intended at all. These two addresses I'm showing you are the same thing. Some people just simply like expressing them in lowercase, and some people like it in uppercase. Again, there's a reminder there. Watch out for any MAC address that's ever shown to you that has a letter in it that comes after F, whether that's on your exam or in network documentation, because someone has mistyped something. I put another address there, and actually you can spot that. I think I put 2 errors in that one, where it's got 1G at the very beginning and then 5T at the end. That's an invalid address. You literally could not put that on a NIC. And another clarification I want to make for you, you can express MAC addresses either with colons, with dashes, or using what we call a dotted decimal. And I personally prefer it with dashes, and that's the way I see it most of the time. That's the way I presented it to you here. But the addresses that I put in the last line there, they're all the same address. It's just a different format of expressing them. Since we've just discussed what a MAC broadcast is, or an L2 broadcast, I'm going to introduce you to your first one as we talk about the Address Resolution Protocol, ARP. And we've got a long example here coming up, an illustrated example. So don't think there are only 2 little things here you need to know about ARP. I don't want to give you a false sense of security there. We're going to walk through an example of how ARP works, because the theory can sound a little odd. But what exactly is getting resolved by ARP in the first place is a known IP address being resolved to a MAC address. ARP is going to come in handy when a PC knows the IP address of the host it wants to send data to, but does not know its MAC address. And again, just as a reminder from the beginning of this video, that source, that host, has to have a destination MAC and a destination IP address to successfully send the data. So again, ARP allows a device to acquire the MAC address of a remote host when only the IP address of that remote host is known. And in the example I'm going to show you here, we're really concentrating on the MAC addresses in this video. So what we're going to do is assume that host A already has the IP address of host B. And in this particular scenario, I've put the 3 hosts on a shared segment. You know what topology that is, right? Just by looking at it? That's a bus topology. It's a shared network segment. The reason I do that, even though you don't see many bus topologies these days, is that the operation of ARP is impacted by certain network connectivity devices. So as we walk through these examples, I'm going to change the device that's connecting these hosts. We're going to use a hub, we're going to use a switch, we're going to use a router, but for right now, I really want you to notice that what's going on here is that we are using a bus topology. We're using a shared segment for 3 hosts. So host A wants to send data to 172.12.1.1, and it knows that that is host B's IP address. That's the assumption we're making here. Notice the address, the MAC destination address of the ARP request, and it's all Fs. That is a layer 2 broadcast. So both of the hosts on this segment are going to get this because it is a broadcast, but only B will respond. But before that, there's one other thing A would do, and that is to check its own ARP cache. PCs, much like the one we're working on right now, from host A's point of view, they're going to keep an ARP cache. So host A, there's a possibility before this happens, before that ARP request goes out, that host A may already know host B's MAC address. So excuse all the extra prompts there. Let's move that down. We've got a complete section coming up later, a complete video on workstation troubleshooting commands, and we will go over the ARP commands again there, but this is a good introduction for you. ARP-A will display the ARP cache. It's going to show you the MAC addresses and the IP address mappings that the PC already knows about. That's interesting. We're not getting anything. We're not getting a message. And if you're saying, hey, you're doing something wrong, you're right, I am doing something wrong, and I wanted to illustrate this to you now. With Microsoft Workstation troubleshooting, you're going to have a lot of what I call switches, a lot of options, because if we just type ARP and hit enter, this actually gives us ARP help. There's nothing wrong with that, because believe me, no one remembers all the syntax for everything. If you learn something right now that you can carry through the rest of your studies, no matter how far you want to go, and through the rest of your career, no one remembers all these commands. You need a little help sometimes, and it's important to know where to find it. And with Microsoft, in the case of ARP command, and most of their commands, if you just type the basic command and hit enter, it's going to show you the options. And you'll notice up here next to -A, which is the top one, displays current ARP entries by interrogating the current protocol data. It sounds very formal, but what it does is it looks in the cache. I guess that wasn't fancy enough for them. And notice what I was doing wrong, though. You don't leave a space between your dash or your hyphen or your minus sign, whatever you want to call it. You don't leave a space between that and the letter that you're using. It's a very common thing to do. And I've done that before. You're not really thinking about it. And the thing is, the PC's not going to give you an error message. It's not going to tell you what you're doing wrong. Cisco would, but Microsoft won't. So there we've got ARP-A, no ARP entries found. So right away, if this were host A would first look in its own ARP cache and say, hey, I don't have any ARP entries at all. I don't have a mapping for that. So I better send an ARP request out. And that's exactly what happens here. So again, this is a layer 2 broadcast. It's going to have a MAC destination of all Fs. And every device on this segment is going to see it. And they will only respond to it if that IP destination of 172.12.1.1 is actually their IP address. So what host A is doing, in effect, is yelling out to the rest of the network, I need the host device with the IP address of 172.12.1.1 to send me your MAC address, because I want to send you some data. And again, since we're working on a shared segment, every host on the segment is going to see that ARP request, but only the host with that IP address will respond. And here, host B is sending an ARP reply to host A saying, here's my MAC address, etc., etc. This is a unicast, because host B is going to see in the ARP request who's requesting it, the IP and MAC address of the host requesting it. So host B knows everything it needs to know about host A. So the ARP request is a broadcast, but the ARP reply is going to be a unicast. And once host A gets that information, it can now transmit data directly to host B, because it knows the IP address and it knows the MAC destination address of host B. And that data would be entered into the ARP cache that we just looked at. So if host A in a few minutes needed to send something else, it could look in its cache, and if that data had not aged out or timed out, left the table, then host A could just send data directly to host B without going through the ARP process. So that's really the basic operation of ARP. You can see that it's actually very simple. And of course, we need to complicate it, right? Because we're in networking. We got to make this a little more complicated. And as I've mentioned a couple times, you don't see many bus topologies anymore. So what we're going to do now is take a look at ARP's operation when we've got other network devices in there, hubs, repeaters, switches, and routers, because that's much more realistic. Because sometimes ARP is affected when there's an intermediate device between two hosts, and sometimes it's not. So let's take a look at a couple of those situations. Let's take a look at a scenario where we have something separating two hosts, and besides looking at the title bar of this, you should know by looking at that that this is indeed a switch. That's our little square with 4 arrows on top. And that's a universal representation of a switch. So you should be able to see that in network documentation or an exam question and know what the heck that thing is. Now we need to talk about what the heck that thing does as far as ARP is concerned. And one very basic rule of switches is that switches by default will forward a broadcast. And they won't just forward them out one port. If host A sends an ARP request out right now, that ARP request is a layer 2 broadcast. Remember, it's got the all Fs address. So that switch is going to send a copy of that request out every single port on the switch except the one it came in on. And if you think that's a lot of unnecessary traffic, you're onto something there. And we're going to talk about that in the switching chapter. Because as I mentioned, broadcasts sound like a great idea, but we don't want them just going all over our network and taking up bandwidth that they don't need to be taking up. So just want to introduce you to that concept very early here in your studies, and we'll talk about it more in the switching video itself. So if we had, and this can happen, you've got switches out there that have 80 ports, you've got switches out there that have 96 ports, possibly more on the way. Let's say that you had even just 48 hosts connected to the switch. Well, when one of those hosts sends an ARP request, by default, all of the other hosts, all 47 of them, are going to get a copy of that. Now, the only one that will respond is B, but again, that's a lot of traffic that's going to be going around. So, to sum it all up, with a switch, there is really no impact as far as the operation of ARP is concerned. If host A sends a request out, and again it's broadcast to the all Fs address, every other host connected to that switch is going to get it. And host B will see the request and say, okay, that's my IP address it's referring to, so I will respond to this with my MAC address. And the ARP reply is going to be a unicast because that ARP request will contain the IP and MAC addresses of host A. So host B doesn't have to send out an ARP request in order to respond to an ARP request. So with switches, no problem. ARP is going to work just perfectly fine. Now switches work at layer 2 of the OSI model. Let's discuss quickly two devices that work at layer 1 of the OSI model. And those are hubs and repeaters. And you've got hubs that can do a little more than what I'm about to describe, but at its base, a hub is a multi-port repeater. And what a repeater does is it takes an incoming data signal, the electrical signal, all those ones and zeros, makes a new copy of the incoming data and sends out a fresh signal. It regenerates it, if you will. It's going to send out a strong copy of it. What repeaters allow us to do when we need them is to extend the maximum segment length of part of our network. Repeaters are just about gone. They're still out there in a few older networks, but that's what repeaters do. So repeaters and hubs both work at layer 1 of the OSI model. They are physical devices, and what the physical layer devices, that is. And they have absolutely no effect on ARP or on anything else. So if you get any questions in the exam or on a job interview or you're reading documentation and you wonder, I wonder how a hub or a repeater will affect this, it won't. The only thing those devices do is strengthen the signal and send a fresh copy of it out. So with ARP so far, we know that a hub has no effect on it. We know that a repeater has no effect on it. We know now that switches forward broadcast by default. So a lot of devices that don't need it will get the ARP request, but the one host that does need it, host B, the one we're trying to get it to, will receive it with no trouble at all. And this is a very typical local area network setup. If you've got two hosts in the same building that need to communicate, you're just going to have switches between them. You're not going to have routers. But what happens if we get a router involved? Let's take a look at that. Now we're getting a little more complex. We've got a little more of a realistic connection between two PCs that are not in the same building, because we've got two switches involved here, but we also have a router, and that's the universal symbol for a router, is that round disc-like thing with 4 arrows on top of it. And here host A wants to send data to host B, and it does not have host B's MAC address, but it does have host B's IP address. Well, we haven't covered routers in detail yet in this course, but this is a good place to introduce you to a basic routing fact. By default, routers do not forward broadcasts. Switches do, but routers do not. Now, the good thing is a router will accept a broadcast. There's a little misconception there among some exam candidates. Routers accept broadcasts, and as you'll see, routers can actually generate broadcasts, but they do not forward them. They do not receive a broadcast on one port and then send them out all the others. That's not going to happen. So here then, we've got a little bit of a problem, because as you know now, an ARP request is a broadcast. And it's going to go through the switch with no problem at all, as the arrow indicates. Switches, no problem. So it gets forwarded to the router, and I put a little stop sign there to show you that that's where the process stops, but the router does accept the ARP request on E0. That's the Ethernet 0 port. On the other side, we've got an Ethernet 1 port. So the router accepts it, sees that it's a broadcast, and says, sorry, I can't send this on anywhere. So the problem here is that host B cannot possibly get the ARP request from host A. Cannot happen. So what are we going to do? Well, what we have to have running on that router is a service called Proxy ARP. And if you're not familiar with the term proxy, it's often applied to a vote, a proxy vote. And what happens is someone else casts a vote on your behalf because you can't be there, and that's a proxy. Well, what a proxy is in networking here, and with Proxy ARP, is that the router is going to respond to the ARP request on behalf of host B. And that's a Proxy ARP reply. Now, the tricky thing here is that the Proxy ARP reply is not going to contain the MAC address of host B. What it's going to contain is the MAC address of the router interface that received the request originally. So what happens again is that the router sends a Proxy ARP reply, and that reply contains the MAC address of the router's Ethernet 0 interface. It is not the interface that leads to host B, which is E1, and it is not the MAC address on host B itself. It's going to be the MAC address of the router interface that received the request. And that's pretty cool, man. That's the only way we can get it to work, is with Proxy ARP. And the real beauty of this, of Proxy ARP, is that the entire process is transparent from host A's point of view. Host A just wants a destination MAC address. It doesn't have any way to verify, okay, I know this is host B's MAC address. It just needs a destination MAC. So host A has no idea that the MAC address it just received as a result of its ARP request is actually the MAC address of the Ethernet 0 interface on the router. And as far as host A is concerned, it has the MAC address of host B, the MAC address it needs. So we have a very unusual scenario here, and this is not just good for your Network Plus exam. When you go into the CCNA, this little bit will come in handy, so you can consider this a preview, if you will, that now when host A sends data to host B, the destination IP address will be that of host B, but the destination MAC address is going to be the MAC address on the router's Ethernet 0 interface. So that's something you have to get used to with layer 2 addressing anytime ARP is concerned with and there's a router in there, is that when data ends up leaving host A, the IP address is always going to be the IP address of the final destination. That is not going to change. But the MAC address destination may change as the data goes across the network. So that's where Proxy ARP comes in. And if your head's spinning a little bit with that, it's an unusual concept. I do understand. So what we're going to do is walk through an example using this particular network topology, but we're actually going to throw the IP addresses in and watch what happens. So again, there's a graphic of what would actually happen at the end of the example we just went through. When host A actually begins transmitting to host B, the IP destination address is indeed host B's IP address, but the MAC destination address will actually be the MAC address of the router's Ethernet 0 interface. Let's walk through an example of that and actually use some different MAC addresses, because I'll be the first to say when you first hear about Proxy ARP, you go, well, you know, is that really going to work? Well, this is how it works. Assuming, again, that host A already knows host B's IP address, it's got to have host B's MAC address. And you see here, we actually have 3 MAC addresses in the diagram. We've got one on Ethernet 0 router interface. We've got one on Ethernet 1 router interface. And you can see the MAC addresses are different. And, of course, host B's MAC address is all B's. So host A is going to do the usual thing. It's going to send out an ARP request. And what's the destination of that again? You should actually be able right now to look at that and tell me, or CompTIA, what the destination IP address and what the destination MAC address would be of this ARP request. I'm sure you can. There it is. The IP destination is 172.12.1.1. The MAC destination is the all F's address, the layer 2 broadcast. So there will be no problem with that first switch. No problem at all. The ARP request is going to go right through that switch with no problem at all. And we'll angle that arrow up to indicate that it's now going up to the router interface. The router will accept this packet, this ARP request, and it's going to look at it and say, oh, this is a broadcast. I can't forward it, but since I have Proxy ARP working, then I can answer it. So what the router will do, you can see I put a stop on the other side this time, just to remind you, the ARP request is going to be accepted. It's just not going to be forwarded. It's not going to be sent out E1. So the router sends a Proxy ARP reply. And by the way, the ARP reply and the Proxy ARP reply look exactly the same to host A. It doesn't say actually proxy inside the reply. It's just simply going to say, okay, you know, I'm your guy, and here's my MAC address of all 2s. So now, at that point, when host A starts sending data, then it will indeed have, let's go back there, yep, same thing. The IP destination will be that of host B, and that will always be the case. The MAC destination address is going to be the E0 MAC address. And with Proxy ARP, this is going a little beyond your exam material here. Most routers have Proxy ARP enabled by default. That is not always the case. With a Cisco router, it's a little command called IP Proxy ARP, and you can look at the configuration on a router. If you don't work in the WAN department of your network, maybe you can get a guy in there or a gal to show you the configuration of a router, and you can see whether Proxy ARP is running on it or not. But not all routers have that service enabled by default, and if you don't need it, you can always just turn it off. But that's what Proxy ARP does for us. Before we discuss reverse ARP, which you'll be happy to hear is nowhere near as complicated as Proxy ARP can be, let's take a quick look here at ARP and intermediate network devices again. Just to repeat, no pun intended, that repeaters, hubs, and switches do not affect ARP operations in the least. That's because switches forward broadcasts. Routers do affect our operation because routers do not forward broadcast. Proxy ARP was designed for just that purpose. The router is going to answer the ARP request with the MAC address of the interface that received the request, and at that point, the host has a destination MAC. It has no idea that it's not the MAC address of the intended destination, but it's going to send the data with the IP address of the intended destination, and the MAC address destination is actually going to be that on the router, the closest router interface. So we're going to review all this again in just a few minutes, because this is all important stuff, and I know if it's the first time you've seen it, it can be a little overwhelming. But we're going to take a look at a review of this after we take a look at reverse ARP. And reverse ARP, or RARP, or RARP, if you want to pronounce it that way, you really don't see much of this anymore, and you'll see why as the course goes on and we talk about DHCP. If you already know about DHCP and how it operates, that's really one of our two dynamic IP address assignment protocols, and it's much more popular than reverse ARP. It has many more features than reverse ARP does. But what reverse ARP does is it resolves a MAC address to an IP address, but it has nothing to do with a remote host. It has nothing to do with another host. What happens is a workstation boots up, and it's going to see its own MAC address. If it doesn't see its own MAC address, we have big problems right off the bat. But it's going to see its own MAC address, and it's going to keep booting up and says, wait a minute, I don't have an IP address statically configured. I better ask for one. So once the workstation finishes booting up, if it is configured to use reverse ARP, then it's going to send a reverse ARP request containing its own MAC address, and it is a broadcast and says, hey, I need somebody to tell me what my IP address is. And a reverse ARP server will hear that request and answer it with an IP address. And again, if you already know about DHCP, this is going to sound really familiar. If you don't worry about it. You'll definitely know all about it before we're done with this course. But reverse ARP and DHCP are both dynamic IP address assignment protocols. It's very rare in today's networks that every workstation is going to have a statically configured IP address that either you or I as network admins went to and entered. What we usually do is just configure it to get its address dynamically. If you have a broadband connection at home, or even a dial-up, when you connect to your internet service provider, you're going to be given a dynamic address. And that will expire after a while, but it's much more efficient than trying to just give you an IP address, because then when you're not on the network, an address is being wasted. So again, reverse ARP, you see it in some Unix environments still. It plays better with Unix than DHCP does, but still, it's very rare that you'll actually see it. But a couple of differences between ARP and reverse ARP. Not only what they resolve, I'd be really familiar with that, as I know you will be. But keep in mind that with reverse ARP doesn't have anything to do with communications with another host. Nothing at all. It's the workstation itself, the local workstation booting up and saying, you know, hey, I don't have an IP address, I got to get one. And if that workstation is configured to use reverse ARP to do so, then it sends that request, and a reverse ARP server will answer it. So let's take a quick review here and some exam tips that I think can help you out. Just some things I would know walking into the exam room, and also for real-world networks as well. You really want to know the different names for MAC addresses and what they're referring to, if they call it a physical address or a hardware address. You tend to hear those more around network rooms than you would in an exam room. But just in case, you know, MAC, L2, Layer 2, physical hardware, and burned-in address, or BIA, those are all names for a MAC address. You must know the format of a MAC address and what what each does. The first half of the address is the OUI, the organizationally unique identifier. That's assigned to one vendor and one vendor only. The second half of the address is the device ID, and that is simply a combination of hex values that that particular vendor has not used yet with that particular OUI. You certainly know what the MAC address, broadcast address is, as I put it there. The all F's address. Either in the exam room or in documentation, I guarantee you one day you're going to see a MAC address that somebody mistyped. because something I'm going to fill you in on right now, not everybody in this business is a really good typist, especially when it comes to the numbers. That really seems to frazzle a lot of us. You don't have to be a great typist, but you have to be an accurate one. We're in the business of letters and numbers here, so it doesn't matter how fast you do it, but you got to do it well. And if you ever see a MAC address with anything with a letter that comes after F, someone has mistyped something or they're trying to pull a fast one on you. And we don't want either one of those things to happen. Again, in ARP review, ARP resolves an IP address to a MAC address, and again, that is the MAC address of a remote device. It's not going to be the local device. If a PC boots up and it doesn't know its own MAC address, it's in trouble. It's got a bad NIC. Something else is wrong with it. But ARP is resolving an IP address of a remote device to the MAC address of the remote device. Again, there's our all Fs broadcast. That's what an ARP request is. The ARP reply is going to be unicast. Hubs, repeaters, and switches do not affect the operation of ARP. Routers do, because they don't forward broadcast. So a router can use Proxy ARP to answer that ARP request on behalf of the intended destination. And the Proxy ARP reply is going to contain the MAC of the router interface that received the ARP request. And the entire Proxy ARP process is transparent to the requesting host. That's a term you'll bump into a great deal in networking, is transparent, and that just means the host doesn't know about it. That's all we mean by that. And just one more mention here, reverse ARP and what it does. It is one of two dynamic IP address assignment protocols. And reverse ARP allows a workstation to request an IP address when it only knows its MAC address. There we go. So it's a MAC address that we're looking at there. Reverse ARP, again, I'm just comparing the two there for you. It resolves a MAC address to an IP address. The MAC address is known, the IP address is not, and of course that is on the local workstation. ARP is going to take a known IP address and resolve it to a MAC address of a remote device. So I hope you've enjoyed this particular part of the course. If this is your first exposure to ARP and Proxy ARP, I would make sure to watch the video, frankly, 2 or 3 times. Make sure that you are very, very good with the basics of ARP and Proxy ARP. And that about wraps it up for this particular video, and I'll see you on the next one.